Welcome students to this new lecture of digital communication. So in this lecture we will start talking about M-ary phase shift keying. So in the previous video we started discussing about your M-ary signaling techniques in general, and then we were discussing about M-ary ASK. Okay, so we were talking about M-ASK. So in this lecture we will talk about M-PSK. So the general expression for a signal in an M-PSK is given by this. So SIT, where I can be from 1 to M. So the general ith signal looks like this. So the amplitude is constant here, because we are now interested only in the phase, because we are doing PSK. So so inside this cosine wave we have the carrier frequency and then a constantly varying phase which is a function of I. So the ith signal has a phase difference that is proportionate to I. Okay, so so essentially when your I is 1, then you have no phase difference, it's just a cosine wave. Okay, so your S1 is a cosine, plain cosine wave. Okay, your S2 will be so I minus 1 is 2 minus 1, that is then 2 pi over m. So V of cosine 2 pi fct minus 2 pi by m, and so on. Finally your Sm will be your V cos 2 pi fct minus m minus 1 over m times twice pi. Okay, so so this is your general structure of the M-ary phase shift keying signal. The signal can also be written as this. So you expand this trigonometric identity and you will get this expression. So here you can see that if you write in this way, and if your V, the amplitude, can be written in terms of the energy. So your energy of the signal, of any signal, the ith signal or any signal, is V square Ts by 2. Okay, so where V is the amplitude and Ts is the symbol duration. Okay, so you can write V in terms of square root of twice Es over Ts. Okay, so if you write V in this expression in terms of this Es, then you can see that you can basically use this cosine and the sinusoidal carriers. You can use them as the basis functions, so the orthonormal basis functions, and you can write the ith signal in terms of this basis function. So if you define the orthonormal basis in terms of the cosine and the sine part of the signal, of course they should be normalized by dividing with the square root of energy. Then you can write the signal SIT as square root of Es time cosine of I minus 1 times 2 pi by m phi 1 t plus square root of es sine of I minus 1 2 pi over m phi 2t. Okay, so the same expression here can be written like this if you define your orthonormal basis functions like this, and if you check that these two are indeed orthonormal. Okay, if you integrate these two by multiplying them together, then it will be 0 and then they will have unit energy. Both of them will have unit energy. Okay, so essentially these parts are the coefficients of your ith signal. Okay, so the coefficients of the ith signal are given by these. Okay, so if you now plot this, so you can see that this M-ary PSK can also be represented by just two orthonormal basis functions like your QPSK. In your QPSK, you could represent the four signals using two orthonormal basis functions. Here also you can do the same. So whatever be the value of m, you can represent all the m signals in a 2D space defined by phi 1 and phi 2. Okay, and if you plot these different signals, then you will see that all the signals lie on a circle of radius square root of es and are spaced every 2 pi m radians around the cycles. So this is how it will look. So this is a special case of 8 PSK where m equal to 8. Okay, so m equal to 8 means you have 3 bits per symbol. So each of the signal can be represented as a dot on this circle of radius square root of es, and each of them is 2 pi over m apart. So here your m is 8, so this is therefore pi by 4 apart. So each of them are pi by 4 apart, and then you can map the 3 bits of the symbol onto the signals like this. So this S1 corresponds to 000, S2 corresponds to 001, and so on. So you can map all the signals with the combination of 3 bits that you can have, which is exactly equal to 8. Okay, if you have zeros and ones. So this is how you can represent the signals of your M-PSK. So this is the general signal space for the M-PSK. Okay, you could have M signals like this, S1, S2, S3 up to Sm. Okay, and they will be 2 pi by m apart, and the distance from the origin of the signal space to a particular signal is the square root of energy of that signal. So every signal has the same energy, by the way. All of them has an energy Es and an amplitude square root of Es. So so as I said in a previous lecture also, the distance from the origin of the signal space to the signal is actually the amplitude of that signal, and the angle that it makes with the positive direction of the phi 1 axis is the phase of that signal. So that notion is also applicable here. Okay, and the optimum receiver looks similar for M-PSK as in the case of QPSK or binary. and the number of arms of the optimum receiver is purely denoted by the dimension of your signal space. So this is a 2D signal space, and for binary case also you had 2D signal space. For M-PSK also you had 2D signal space. So you had two arms where you are correlating the received signal with phi 1 and phi 2, and you are taking samples every ts seconds to receive the components R1 and R2 of the received signal, and then you are doing the minimum distance decision rule here, and then you are estimating the transmitted symbols. Okay. So now if we want to calculate the probability of error for an M-PSK, let's take the example of 8 PSK here. So, so here you can see if you have this signals which are spaced pi by 4 apart, and if you want to draw the decision boundaries for these, then the decision boundaries are nothing but the perpendicular bisectors of the line joining the two signals. So the decision boundary that separates S1 and S2 is given by this. Okay. The decision boundary between S2 and S3 is given by this. Okay. So similarly we can draw the decision boundaries like this, and then these things extend to the other direction as well. Okay. Okay. So these are your decision boundaries. Okay. And these are the regions for each signal. So this region is R1 for S1. So if your receive signal falls within this region, then you can choose S1. Okay. If your receive signal falls here, this is the region R2 for S2. If your receive signal falls here, then you can choose S2. Similarly, this region is for S3, and if your receive signal falls here, you can choose S3. And that's how you can decide which signal was transmitted. And if for some reason, because of noise, your receive signal falls elsewhere, okay, let's say you have transmitted S1 and your receive signal falls here, then you are making an error. Okay, your receive signal has to fall here to make a correct decision. Okay. So to calculate the probability of error for higher order modulation system, okay, like up to m equal to 4, it was still okay. We saw for M-PSK how we can compute the probability of error. Okay, but for m greater than 4, okay, it becomes a bit difficult. Actually, it becomes difficult to define the probability of error in a closed form expression. Okay. And also it's difficult to calculate so difficult to get a closed form expression and also an exact expression. Okay. I mean both mean the same, closed form expression and exact expression. I'm not saying it is impossible, but it is difficult. Okay. So therefore, in case of higher order modulation, we use some bounds. Okay. So basically, we say that if your probability of error is less than some bound, some maximum value, or it is between two values, okay, let's say the upper bound and let's say the lower bound. Okay. So in this way we get an estimate that your probability of error is within some values. Okay. So let's see what are the bounds, or how can we approximate the probability of error and use these bounds. All right. So the first method is called the union bound. Okay. So here we will be using some of the concepts that we have already learned. So okay. So so consider only the pair of signals. So let's say you have an M-PSK signal space like this. Okay. Where you have different signals, okay, across this circle, S1, S2, S3 and so on. Okay. So now just consider a pair of signals Sk and Sj. Okay. So let me call this as Sk and this as Sj. Okay. So now let's say that Sk is sent and let Ej denote the event that the receiver choose Sj. Okay. So that means if this is your decision boundary between Sk and Sj, you have transmitted Sk and your received signal falls in this area. Okay, because of noise. So you are choosing Sj since your received signal is falling in this region. Okay, and that is a event where an error is happening, and we are calling that event as Ej. Okay, so Ej denote the event that the receiver chooses Sj, hence making an error. So therefore the probability of Ej is the probability of error due to Sk and Sj. Okay. So so the probability of symbol error for Sk is therefore denoted as this, okay, which is the union of all these Ej's. Okay. So if you are transmitting Sk, then all the error events are counted like this. If your received signal falls within Sk, then that is not an error. Okay. If your received signal falls here, but if your received signal falls here or anywhere within the decision region of the other signals, other j signals which are not equal to k, then you are making an error. Okay. And the probability of symbol error for Sk, which is the error when Sk is transmitted, can be denoted as the union of all such events. Okay. So union of all these pairwise probability of errors. Okay. P probability of choosing Sj when Sk was sent. Okay. So the union bound on this particular expression is basically this. So if you recall from your lectures on probability theory, which we did during week 1 of this module, then you might recall that probability of union of some events is less than or equal to the sum of those probabilities. So basically this comes directly from the fact that probability of A union B union C is less than or equal to probability of A plus probability of B plus probability of C. Okay. So this result is used here. Okay. And this will be exactly equal. This inequality becomes equality when these events are mutually exclusive, which means if you have A intersection B as an empty set, B intersection C as an empty set, and A intersection C as an empty set. So if they are not overlapping, then the equality holds. But in general, the probability of unions is less than or equal to the sum of the individual probabilities. And we have used that union bound here. So this probability of symbol error when Sk is transmitted is less than or equal to the pairwise probability between Sk and Sj. Okay, and the pairwise probabilities are these. Okay, so when Sk is sent, what is the probability that you choose Sj? Okay, so now from here we can write that if all the SIs are equally likely, okay, then your probability, final probability of error is basically the average of all these probabilities. Okay, so probability of symbol error for one signal Sk is this. Okay, if you average over all k's where you have all the m signals, then you have this. If all the SIs are equally likely, then you have 1 over m, k equals to 1 to m, and then you sum over all these probabilities. And these probabilities have this bound here. So I now put this bound here and we get Pm less than equal to 1 over m, sum over all m's, sum over all j not equal to k, probability of Sk comma Sj. Okay, so now what is probability of Sk and Sj, this thing? So if you recall, if we have two signals, okay, let's say this is Sk and this is Sj. Okay, let's say this is my signal space and I have two signals here. Okay, so if you recall again from whatever you have learned so far, that probability of error between two signals is basically the Q function of the distance between the two signals okay, divided by the noise RMS bandwidth, okay, which is given by square root of 2n0. Okay, so sorry, noise RMS power, I said bandwidth, but no, noise RMS power. So distance between the two signals divided by the noise RMS power. Q function of this ratio gives you the probability of error between the two signals. So if you just consider Sk and Sj, you have two signals, you sent Sk and you are choosing Sj, therefore making an error. So this error is nothing but this Q function of the distance between the two signals, okay, divided by square root of 2n0, and if you take everything under the square root, then you have d square kj divided by 2n0. So d square kj is basically the distance between the two signals. So this is the distance between Sk and Sj. Okay, so now if you now use this expression in the okay, before that, before using that expression, let's let's do another thing. So note that qx decreases with x. Okay, so you have your x and you have your qx here. So it's a decreasing function like this. You have seen this curve many times by now. So a further upper bound can be obtained by using the minimum distance d mean, which is the minimum of all possible dkj's. Okay, so if you have, let's say, 8 signals, let's consider 8 PSK. Let's consider 8 PSK, and then if you have 8 signals S1, S2 up to S8, then you calculate the pairwise distance between each pair of signals. So you calculate D12, okay, you calculate D13 and so on up to D, let's say 18, and then everything, all possible pairs. So if you have 8 signals, then you will have 8 into 8 minus 1 pairs, so that is 56. So you have to calculate 56 such distances. Okay, for m signals, this will be m into m minus 1. Okay, so if you calculate all these distances and you take the minimum of those distances over all j and k and define it as d mean, then this PSK can be written as this. Okay, so since your d mean is always less than any of these dkj's, because d mean is the minimum of these dkj's, so d mean will be less than equal to dkj for all k and j. Okay, so that then you can use this property of the Q function. So this numerator is always greater than this numerator. Okay, and therefore the Q function involving dkj is always less than or equal to the Q function involving d mean. So you can say that your PSK is less than equal to Q of the square root of d mean square over 2 and 0. Okay, now if you replace this in the original formula, so the original formula was what? The original formula was this. Okay, so this was the original formula. So let me let me write it for you in the whiteboard here. So the original probability of error, denoted by Pm, is 1 over m. Okay, sum of k equal to 1 to m, then this sum where your j not equal to k, probability of sk sj. Okay, and probability of sk sj is nothing but the Q function of the distance between the two signals divided by square root of twice n0. Okay, and this you can write as this. Okay, and since your d mean is the minimum over all k and j of dkj, so any dkj will be less than or equal to d mean. Okay, so sorry, greater than equal to, so d mean is less than equal to dkj for all kj's. Okay, so then you can write this because of the property of the Q function, which says that as x increases, your qx falls sharply like this. So you can say that this is basically less than equal to d mean square by twice of n0. Okay. So now if you plug this here, then you get Pm equal to 1 over m sum over all m, and then you plug this value, and this is j not equal to k, and then you have this value d mean square by twice n0. So the equality becomes the inequality now. Okay. So then you can see that this is for all j not equal to k. Okay, and this is a constant term. This q of square root of d mean square over 2n0 is a constant term. It doesn't depend on j and k. Okay, but then you are summing it over all k and all j not equal to k. So this sum runs m times m minus 1. Okay, so you can write this as 1 over m, and then this entire sum runs over m times m minus 1 of this q function. Right. So then this m cancels, so you can write the probability of error of a M-PSK system is less than equal to this value. Okay, so this is your union bound. Okay, so that's what you have here in this slide. Okay, this is the final expression for the probability of error. Of course, approximate value, not the exact expression, but the approximate expression for your probability of error is this, which roughly gives you the value of the probability of error. And we have derived this using the union bound. Okay. So there is another approximation called nearest neighbor approximation. So here what happens is that you start with this as you did in the previous case, but now you can replace this part with this part. Okay, so this part says that you can replace this pairwise probabilities, the sum of these pairwise probabilities, with a term n d mean comma k times the q function of the square root of d mean square over twice n0. And n d mean k is basically the number of signals at a distance d mean from sk. Okay. So in case of union bound, what was happening is that, imagine the case of the 8-PSK, so you have 8 signals like this. Okay, so you have all these 8 signals, and using the union bound, you are calculating all these pairwise distances. Okay, and for each signal you are calculating the 7 other pairwise distances, and then for 8 signals you are getting 56 distances. Okay, So that was union bound, and then you plug in to the formula that we just derived. Here in case of nearest neighbor approximation, what you are doing is that you take this signal S1, okay, and you see what are the nearest neighbor. Let's say if your D mean is this, clearly you can see from this signal space diagram that your D mean is the distance between two signals, two adjacent signals. So between S1 and S2, whatever is that distance, that's your D mean. Between S2 and S3, whatever is that distance, that's your D mean. So all you need to do here is to check how many nearest neighbors you have. So for example, in this case, S1 has two nearest neighbors, S2 and S8. So these are the only signals that are within a distance D mean from S1. Okay. So here you are calculating D mean and you are checking what are the nearest neighbors. So your number of calculations are getting much more reduced here in case of nearest neighbor approximation. Okay. And why this sum is approximated by this, okay, this I will discuss later in a live session, okay, or I will also encourage you to think about this, okay, why this can be approximated by this, okay. So in case of a large number of signals M, this approximation is quite true, okay. So you can have the union bound, okay, starting from this, and then you can also have the nearest neighbor approximation as well, and you can calculate an approximate value of the probability of error, okay, and you can comment that the probability of error lies between certain range of values. All right. So let's apply what we have learned so far for the QPSK, okay. So QPSK, we already derived the probability of error when we were doing QPSK. So probability of symbol error for QPSK was roughly twice of Q, okay, was this value, okay, minus Q square this, and then we argued that for high SNR this value is so small that we can write approximately that this is right. So mind you, what we calculate using union bound and nearest neighbor is always the symbol error probability, not the bit error probability, okay. This is always the symbol error. And if you are applying the union bound and nearest neighbor for a binary case, which we normally don't do, because in the binary case you can calculate the exact value easily, but even if you are applying, then for binary you are getting directly the bit error rate, okay, because one symbol in binary is equivalent to one bit, but for other higher modulation schemes one symbol is usually more than one bit, okay. So always we are calculating symbol error probability, okay. So for QPSK, if we apply the union bound, the first thing is that we have to find what is your D mean, okay. So for QPSK, your D mean is this, okay. It's basically the distance between the two signal, okay. And if you see, this distance is square root of ES, this distance is square root of ES, so you can easily calculate this distance, which is the square root of the square of these two. Okay, so ES plus ES twice ES, and then you have d mean, which is square root of twice ES. Okay. So now if you apply union bound for QPSK, then you get this value. Okay. If you apply nearest neighbor, then you get this value. So the actual value is this. Okay. So and nearest neighbor is predicting the actual value very closely. You see, it's less than or equal to twice q of this term, and we indeed have almost equal to twice q of this term. Okay, if we imagine this term, then because of this minus, it's actually less than or equal to twice q of this term. Okay, and your union bound also not bad. It gives you a bound, so this is less than or equal to thrice q. So of course this value is within the bound that union bound is predicting. Okay, so see how for QPSK what we actually calculated matches with the bounds that we have learned right now, and for higher order modulation schemes for m equal to 8, 16, okay, 8, 16, whatever, 32, whatever, you can easily apply this union bound and nearest neighbor and find out an estimate or an approximation of the probability of error. Okay, so let's do an example to make the concepts clearer. Okay, so we can have an example like this. So consider a digital communication system communicating over an AWGN channel using these signals. So the signals are given in time domain. Okay, and the power spectral density of the noise is given. Okay, so this is basically your N0. So assume maximum likelihood detection, determine the error probability bound using the union bound and nearest neighbor approximation. So when we are applying the union bound and nearest neighbor, you see that how these bounds are dependent on the distance between the signals. Okay, or rather d mean. Okay, so the first step for any problem that asks you to calculate the error probability bound using any of these approximation, the first step is to calculate d mean. Okay, so now for this set of signals, let's see what will be the d mean. So you can calculate d mean by plotting these signals in the signal space. Let's say if the signals are given in time domain, then you can apply Gram-Schmidt procedure and find the relative positions of the signals in, let's say, the signal space, and then you can calculate the distances, but that will take you a lot of time. You can directly calculate the distances using this formula. Okay, so if these two signals are vectors, okay, then the distances are actually the distance square. Okay, the distance square are calculated by integrating the difference square of the signals. Okay, so S1, distance between S1 and S2, D12 square is calculated as this. Okay, and D34, so D1 and D2, I mean S1 and S2 are these, and S3 and S4 are just the negative of S1 and S2 respectively. Okay, so S3 is minus of S1t and S4t is minus of S2t. So therefore the distance between 1 and 2 is same as 3 and 4, and that counts as 4. So this distance D12 equal to D34 is 2. Similarly, D14 is also 2, and D23 is also 2. Okay. Now D13, this is also 2, so D13 is 2, and D24 is square root of 12, so that is 2 root 3. Okay. So you can see you calculated all the distances, and the minimum distance D mean is 2. Okay, out of all these calculated distances. Okay, so your D mean is 2, and then you can use the union bound and calculate this expression. So they have 4 signals, so 3q over 4, and then you can use the q function table to find out what is q4, and then you will get this expression. This is your upper bound for the probability of error. Okay. You can apply the nearest neighbor also. So that was union bound for you. The nearest neighbor can be applied like this. So let's say if n1 is the nearest neighbors of signal 1 and n3 is the nearest neighbors of signal 3, then that number is 3. Okay. Number of signals that are within D mean distance. Okay, and n2 and n4 is 2. Okay. So, and you can calculate that from this value of D mean. So you can see that D mean is 2. So therefore, if you calculate n1, which is the number of signals closer or nearest neighbors to 1, so this is 3 is nearest neighbor to 1, because D13 is 2, that is equal to D mean. Okay, and then here 2 is the nearest neighbor and 4 is the nearest neighbor to 1. So there are 3 nearest neighbors to n1. Similarly, you can calculate the other nearest neighbors, and for n2 and n4 this is 2. So then you can use the nearest neighbor formula and you can obtain this expression. So see, union bound gave us 9 into 10 to the power minus 5. Nearest neighbor gave us 7.92 into 10 to the power minus 5. So nearest neighbor always gives you a better approximation, a more tighter value to the exact value. Okay. So so now I will move on with the M-ary quadrature amplitude modulation scheme. So basically you learned so far M-ASK and M-PSK. Now if you combine this together you get M-QAM basically. Okay, so in M-ASK your signals were varying in amplitude. In M-PSK the signals were varying in phase. Now you can have both of them varying and you can get an M-QAM constellation. Okay, so so if you have a two-dimensional signal space defined by this phi I and phi q, so you have this cosine function and the sine function. This is equivalent to phi 1 and phi 2, but we call it I and q to say that this is in phase and quadrature. So you remember we also applied this concept when we were doing QPSK. So we have this in phase and we had this quadrature components. So here also we have these two axes which are the two basis functions given by this cosine and sinusoidal waveforms, and we can define them as in phase and quadrature components. Then the ith M-QAM signal can be represented as this. Okay, so V I and VQI. Okay, and then you can combine them and write it in a amplitude and phase format, where you can see that the amplitude is also dependent on I and the phase is also dependent on I. Okay, so that is why this is called QAM, where you have both ASK and PSK involved. Okay, so this VII and VIQ are the information bearing discrete amplitudes of the two quadrature carriers. Okay, and you can write the energy EI as VQI square plus VII square, and theta I is the angle which can be defined by tan inverse VQI over VII. So basically, if you have these two axes, okay, let's say, so any point on this signal space, okay, can have the component V. So the coordinates, let's say, or the components, whatever, you can say VII and VQI. So basically the x axis of the phi I axis is VII, and the phi q axis is VQI. And then this is the energy, I mean this distance is the square root of the energy. So this is given by square root of EI. Okay, so EI is nothing but VII square plus VQI square, and the angle that it is making with the positive direction of the phi I axis is the phase of this signal, and that is given by tan inverse VQI divided by VII. Okay, so you can have different constellations of a M-QAM like this. So you can have a rectangular constellation where you have 4 signals like this. You can have a constellation like this. You can have a circular constellation. You can have triangular. Essentially, you can have a constellation of any shape. Okay, and your signals are at these points, and depending on where they are in the signal space, they have a unique energy, okay, or a unique amplitude and a unique angle or phase. Okay, and therefore the ith signal, where I can be anything, is defined by both a varying amplitude and a varying phase, and we can have a QAM like this. So you can have many different randomly looking, arbitrarily looking constellations like this. Okay, so you can have any constellations, but the rectangular constellation is the most common or most popular because this can be produced very simply. Okay, so why is that? So the rectangular constellation can be formed in a similar way as we formed the QPSK. So we can have all the information bits demultiplexed into the even number of bits and the odd number of bits, or we can say in phase and quadrature. Okay, so if you remember, we did for QPSK, we were dividing the information bits into in phase and quadrature. Okay, so same thing can be done here, and you can imagine that each of these arm is an independent ASK. Okay, so so you can so your lambda is log of m to the base 2. Okay, so basically depending on how many signals you have or how many levels you have these many bits per symbol. So if your m is, let's say, 16, Then you have 4 bits per symbol, and those 4 bits can be divided into lambda I in phase bits and lambda q quadrature bits. So you can have, let's say, 2 in phase bits and 2 quadrature bits, and you can get 4 for m equal to 16. For QPSK, let's say your m was 4, okay, and you can have your m was 4 and your lambda was 2, and you are having 1 in phase bit and 1 quadrature bit, so you are making it 2 for QPSK. Okay, for general QAM you can do this, lambda I and lambda q. So the lambda I number of bits are, you know, amplitude shift keyed in this arm, and the lambda q number of bits are amplitude shift keying in this arm. Okay, so you have basically dividing the m into m by 2 ASKs. You are dividing the M-QAM into 2 m by 2 ASK, and whatever is appearing, so the m by 2 that is appearing in this arm is 90-degree phase shifted to the m by 2 that is appearing in this arm. Okay, so essentially you get a constellation like this, okay, where each point has a unique amplitude and a phase. Okay, and then in the receiver you can just correlate with phi it and phi qt and take samples at every ts seconds, and then you make a decision for the in phase ASK and the quadrature ASK, and then multiplex the 2 bit streams together to form the original stream. Okay, and if m is a perfect square, so if let's say m equal to 16 or 64 or 256 and so on, then you can divide the lambda I or lambda q into exactly half number of bits. So for 16 your lambdas, this will be 4. Okay, so you can have 2 and 2. Okay, for this this is 8, so you can have 4 and 4. For this you have 16, so you can have 8 and 8. Okay, and the error probability for square constellations, so if your m is 4, 16, 64, 256, etc., for square constellation you can calculate the probability of error in the same way as we did for the QPSK, the probability of symbol error. So this is 1 minus the probability of correct, and probability of correct is the probability that none of the bits that are coming from these two arms are in error. Okay, so neither the in phase ASK has an error nor the quadrature ASK has an error. And for square constellation, the in phase ASK is basically an m by 2 ASK, and the quadrature ASK is also an m by 2 a square root of m ASK. Okay, so so if you have 16, then this is a 4 ASK and this is a 4 ASK. If you have 64, then this is a 8 ASK and this is an 8 ASK. So for square constellation, the probability of correct is basically 1 minus the probability of error for a square root of m ASK. Okay, so this is the thing. Okay, and square of that, because you have two independent arms here, so this part will give you a probability of error like this. Okay, so probability of correct from this section is 1 minus this, okay, and from this section is also 1 minus the error. Okay, so this is again essentially the concept is same as M-PSK, while we are calculating the probability of correct of the two independent arms, and then the probability of correct because of these two arms is the multiplication of these two. So you have 1 minus this error square, okay, and then the overall probability of error is 1 minus this term, okay. So this is a square root of M-ASK, and for square root of M-ASK, if you go back to the lecture notes of your ASK, M-ASK, so this is basically square root of M-ASK, okay. And so if your M is, let's say, 64, then you have to find out the expression of square root of 64, that is 8, the expression of probability of error for an 8 ASK, and the probability of error for a general square root of M-ASK is this. If you look back into the lecture of ASK, M-ASK, then this is the probability of error. So we are replacing M with square root of M there, and we get this expression. You can also get this expression using the union bound, okay, and then you replace this value here to get the probability of error. For general rectangular constellations, this will be the probability of error expression, and you can also obtain this using the bounds that I showed you a little while ago, okay. Now if you want to plot the values of the probability of symbol error for an M-QAM with M, okay, and this is your EB by N0, so you can see that the solid lines are for the exact performance, and the dotted lines are for upper bounds. And when your SNR is quite high, you see in this region for M equal to 16, in this region for M equal to 64, and then mostly in this region for M equal to 256, you can see that as your SNR is high and also your M is high, the exact and the upper bound almost matches, okay. So you see for M equal to 16, when your SNR is low in this region of 5 to 10 dB, there is a gap between the exact and the upper bound, but when your SNR is high, let's say in the region of 15 dB, your exact and upper bounds are quite close, and same for these things, okay. So for high SNR, high signal to noise ratio or high EB by N0, your exact and upper bounds almost coincides, okay. So basically for high SNR approximation, you can use the upper bounds, okay. You don't even need to use the exact expressions, okay. And this slide actually summarizes the performance comparison of M-PSK and M-QAM. So for M-PSK, your approximate probability of error is given by this expression, and for M-QAM you have this upper bound. So if you compare the arguments of the Q function, because the arguments are the ones that are important, then you can make a ratio, and you have this factor called kappa m. So if you take the kappa m in log scale, then with your m increasing, you see that the penalty is also increasing. So you see the numerator is coming from the QAM expression, and the denominator is coming from the PSK expression. So basically kappa m says how is your M-QAM doing with respect to M-PSK. Okay, and as your M increases, this value also increases. Okay, this value rises. So with higher M, the difference between your M-QAM and M-PSK is more pronounced. Okay, so if you have high M, then your M-PSK does almost 10 dB better performance compared to M-QAM. Okay, if your M is 1024, then your M-PSK is better than M-QAM by a factor of almost 22 dB. So this means to generate the same probability of error for a 1024 QAM, okay, it will require 22 dB high power compared to a 1024 PSK. Okay, so this slide shows that PSK or phase shift keying type of modulation schemes are generally better in terms of error probability performance compared to QAMs. Okay, so so let's do an example. So we have this signals constellation where we have 16 equiprobable signals, and using the union bound, find the bound in terms of A and N0 on the error probability for this channel. Determine the average SNR per bit for this channel. Express the bound found in part 1 in terms of average SNR per bit, and compare the power efficiency of this system with the 16 level PAM system. So this is the solution. So basically what we are trying to do is find d mean, and d mean, if you find from this constellation, you will see d mean is twice A, and then you can apply union bound and you find this probability of error expression. Okay, determine the average SNR per bit for this channel. So there are, the total energy is calculated first. Okay, so there are 3 levels of energies are present. Okay, so the signals of this type, okay, the signals of this type, the signals of this type, and the signals of this type. Okay, and then this pattern repeats. Okay, so if you add all of them together, so E1 is A square plus A square. So basically it's for this one, E1. Okay, E2 is A square plus 9A square. So this is for this one and this one. Okay, so this is for E1, these are for E2s, and E3 is the extreme corner. So this is E3. Okay, so you have the total energy for this quadrant is E1 plus twice E2 plus E3, and then this is repeated all over, so you have 4 times this. Okay, so this is the total energy. Okay, and the average energy will be the total energy divided by your the number of these cases. Okay, So you have then this is the average energy, okay, and then the average bit energy is the average symbol energy. This one was the symbol energy that you calculated. So average symbol energy divided by the number of bits in a symbol, which is log 216, that is 4. So you get the average bit energy like this, okay. And and then determine the average SNR per bit for this channel. So the average bit energy is calculated, so average SNR will be EB average divided by N0, okay, and this union bound that we calculated can be expressed in terms of this EB average by N0 like this, okay. So you can replace A square as EB average divided by 2.5, and then you can plug it here and you get this expression. Now for a 16 level PAL, so this is basically PAM, pulse amplitude modulation. So this will be AM. So for a 16 level PAM, this is basically 16 ASK, okay. 16 level PAM is same as 16 ASK. So you can calculate the probability of error of a 16 ASK like this, and then you compare the Q function arguments, okay. So you get the ratio, and you can see that there is a 9.3 dB advantage, okay. So the PSK, the QAM, this is basically a QAM system, okay. So this is 9.3 dB advantageous over 16 ASK or a 16 level PAM, okay. So I'll stop here for this lecture, and I will continue in the next video lecture. Thank you very much.